This is the lesson on virtual CPUs and memory concepts. We will discuss CPU and memory concepts in a virtualized environment. We'll describe what overcommitment of a resource means. We'll identify additional technologies that improve memory virtualization. And we will describe how VMware vSphere symmetric multiprocessing works and how hyperthreading is used by the VM kernel. In the vSphere environment, there are essentially three different layers of memory. The first two layers that you see there in the blue box are within the virtual machine itself. Now, the application layer is actually not a construct of VMware, nor is the operating system actually, but more that's the guest itself. So, how Windows or how Linux manages and handles memory. You may know from other experiences that Windows will take its physical memory and provide a virtual instance of that memory to applications. And the idea behind that is to keep memory within a contiguous space and improve the performance. So the operating system itself has an allocation of physical memory, which in the VM world is actually virtualized as well. And so that's kind of how you see those couple of layers there. Finally, the VMware host itself, the ESXi host, has its own physical memory, which it in turn virtualizes and presents to the operating system, to the guest VMs. And so you can think of the presentation of memory, the physical memory within the ESXi host, to the guest VMs, just in the same manner that an operating system such as Windows presents virtualized memory to an application. And you can actually really just think of a virtual machine as an application that is running on top of an ESXi host. Remember, one of the wonderful things about VMware is being able to overcommit your resources. You can overcommit many things. Right here, we're talking about memory overcommitment. And so the way that memory overcommitment works is, again, you're kind of taking that risk that you may have, I don't know, let's say 8 gigs of memory, of actual physical memory, available on your ESXi host. And let's say you would like to run 8 Windows 7 machines, and you want to allocate 2 gigs of RAM to each of those Windows 7 machines. Well, that's actually 16 gigs of RAM. And so you could do that. You can overcommit, and you're overcommitted by 8 gigs of memory. And so the risk that you're running there is that each of those 8 virtual machines will use up their entire 2 gigabyte allocation. And if they do, you're going to have some trouble. And so that's kind of the risk that you're playing there is, you're going to allow the machines to use as much memory as possible, but there's some downsides if you go over 8 gigs total, if that's your physical memory, and you go over what you actually have physically available. Just as within Windows, there's several things that'll happen. You can hit swap files and all sorts of other things. You can use disk as memory, but then we see huge performance hits. And we'll talk about some of those reclamation techniques that VMware uses in just a little bit. But the one thing to think about is there's a couple different ways that you can actually assign memory to a virtual machine. You can do a memory reservation, or you can just do unreserved memory. And so what that means is if I want to assign 2 gigs of memory to a virtual machine, if I don't create a reservation for that, then a swap file is created, that VSWP. That's the virtual machine swap file. And that is created on the ESXi host itself, and that is a file that sits on the disk, and it represents that machine's memory. And the idea is, since it's not reserved, the ESXi host can't ensure that you're going to actually have physical memory to back that allocation. And so it creates that swap file just to make sure that that memory is available. Otherwise, your guest OS would get host if it tried to use all that memory. So in this particular example here, we're allocating 512 megabytes of memory to these virtual machines. And so we allocate 512 megabytes, and a 512 megabyte vSwap file is created immediately. And the machine runs on, and if the physical memory is not there to support it, then the ESXi host will start swapping that memory out to that vSwap file. Now, if we did a reservation, you can reserve the entire thing or a portion of it. But if we did a full 100% reservation, so a virtual machine that has 512 megabytes of memory, and we do a 100% reservation, so we reserve 512 megabytes of memory for that virtual machine, it's always going to have that actual physical RAM from the host to support it, to back it. And so if we go back to that example I had earlier of 8 machines with 2 gigabytes of memory each, you wouldn't be able to do that if you only had 8 megabytes, or 8 gigabytes of memory available on your host. If you did instead 8 machines with 1 gigabyte of memory each at full reservation, then you would have reserved your entire 8 gigabytes of physical RAM on your host. And what happens is when you power on a machine that has a reservation, it will only power on if the entire reservation is available. So let's say I did have those 8 machines, and I have 8 of those machines with 2 gigabytes of memory each, and they're 100% reserved, and I only have 8 gigabytes of memory on my host. So that's a total of 16 gigabytes of reserved memory. Now I won't be able to power on all 8 of those machines. I'll only be able to power on actually 3. If we just did theoretical numbers, we could say 4. There's overhead that the host itself uses, so you can't use the full 16 gigabytes. Let's just pretend you can for the sake of simplicity, though. So I power on the first machine. It's 2 gigabytes, 100% reserved. Everything's fine. Everything's running great. I power on another one. Now I'm using a total of 4 gigabytes total for my host. I power on the third one. I'm using 6 gigabytes total. I power on the fourth. Again, just theory here. Now I'm using an entire 8 gigabytes. That's the max amount of memory that's physically available. Since all of those are 100% reserved, that memory has to be there. Now when I try to power on the fifth one, it needs another 2 gigabytes of memory. That memory is not available because it wants that full 100% reservation. It needs actually 2 gigabytes of physical memory available for use. And since it's not available, it just won't let it power on. And so that's one of those balances that you do with reserved memory. It kind of takes away from the idea of being able to overcommit, but it ensures that the machine will have that memory available as physical memory. Again, there's other ways to reclaim memory, and we'll talk about that actually just in 1 second. There's swap files and all sorts of fun things, but again, not as robust. You don't get the same performance as you do when you're actually using the physical memory itself. So a lot of times you won't do 100% reservation unless it's a very critical application or very critical server or virtual machine that you're running. Maybe you'll do like a 50% reservation, or a lot of times you don't do a reservation at all. And so if you do like a partial reservation, if we did a 50% reservation, just using the numbers back here on the slide again, if we've allocated 512 megabytes of memory to our virtual machines, to each of these 4 that we see here, and we do like a 50% reservation, so we reserve 256 megabytes of that, that's saying that these machines will not power on unless 256 gigabytes of physical memory is available. So in this case, if we had a host that had 1 gigabyte of memory, all 4 of these machines would power on. 256 reserve, 256 reserve, 256 reserve, and another 256 reserve. That's a full gigabyte. So in theory, those would all power on. Now, since we've allocated 512 but reserved 256, we have to make up that balance. So that extra 256 megabytes of memory in this case would be allocated in the form of a virtual swap file. So that vswap file would exist again, and it's the same size as the difference between the allocation and the reservation. So if we allocate 512 megabytes and we reserve half of that, 256, then your vswap file would be 256 megabytes, and it would take up that memory on your data store where you have it configured. So what are some of the ways that VMware deals with overcommitment of memory? One of the ways to do it is to use transparent page sharing. And what that does is it looks at all of the contents of memory, and it only stores it once. So it's kind of like data deduplication, but instead of on hard drives, it's more in the memory itself. And if you've got, think about it, if you had 4 Windows 7 machines running, there's a lot of information in memory that's exactly the same. If they're all Windows 7 machines, all the same version, there's a lot of things that are in memory that Windows just stores there that it uses for its own use. And so there's going to be a lot of pages within memory that are exactly the same. And rather than burning up all of that memory multiple times, it recognizes that those pages are exactly the same, and it stores it once and then just puts a link or a hook to that memory so that all 4 of those machines, let's say in this case, can share that same location. As soon as the contents change, then it'll write it off to another location. But anything that's identical, it only stores it once. So that saves a lot of memory right there. That's the very first thing that ESXi does to try to conserve memory space. And if that's not working, if that still doesn't save enough memory, then there's also these things are actually kind of out of order here, but there's also another way that it'll do it, and that's deallocating memory from another virtual machine, and that uses the balloon mechanism. Again, you have to have VMware tools installed for this to work, but the balloon mechanism, it installs a driver, and it goes in and it actually tells, or it makes the guest operating system think that it's using more memory than it needs to, and forces the guest operating system itself to start using its own swap file. So not that virtual swap file we talked about, that's within ESXi itself. I'm talking about the actual Windows swap file that all Windows machines have, and Linux machines have them as well. So it forces the machine itself to start swapping to its own page area, and then it frees up that physical memory for another virtual machine. One of the other techniques is memory compression. So it'll go through and it'll just try to compress down some of that memory, look for some of the components that are similar, and use some algorithms to compress that all down. Another one is doing host level SSD swapping. So this is again a similar idea. It's still swapping, but it's a specific swap file that you put on solid state drives, and it's for the host cache. So this is the host cache swap file, and it's very specific. You have to put it on SSDs, and you get that greater performance. It's not on mechanical drives, and this is not the same thing as the virtual swap file that we'll talk about in just a second. That's the last resort, is paging out to the disk. So paging out to that actual vswap file we talked about. That one's there just kind of as a fail-safe, and that's the very last thing that'll happen. Is if none of these other techniques work, then the VM kernel will actually use that vswap file to try to at least provide that memory to the virtual machine. But again, just like within Windows, once you start swapping to disk, things start getting bad. It's poor performance. Okay, so that's memory. Let's look at symmetric multiprocessing and how VMware ESXi handles that. So every CPU, every core, every thread is presented, or can be presented as a CPU. And so in the first example there, we're looking at a single core CPU, physical CPU, single core with two different sockets. So two different CPUs, single core each, and it would be presented as, in this case, we're assuming these are, not hyper-threaded, and I just have a single core each, two different sockets presented as two different CPUs. But we just have a single processor virtual machine, so it just uses up one of those processors. The second one over is a dual processor virtual machine, and you'll see we have only a single processor in the ESXi host, but that single processor has two cores. So it's a dual core single socket system. Each of those cores is presented as an individual virtual CPU available for use by the virtual machine. And then the last one is just kind of the same idea, single socket but quad core. So four CPUs are presented as virtual CPUs to the virtual machine. The virtual machine thinks that those are actual CPUs, single core CPUs. What's more interesting though is when we get into hyperthreading. So when you have a hyperthreaded system, you can have essentially it looks like multiple CPUs per core. And you'll notice this if you look into Windows and you go to your properties and you look at the performance tab, you'll see maybe if you have a dual core hyperthreaded system with a single socket, it'll actually show up as four processors. So you see those four different trending lines, and you only have actually one processor, so there are two cores, but then you have hyperthreading, so it actually shows up as four logical CPUs. That's the LCPU designation there, logical CPU. And so VMware takes advantage of that, and it will actually, in this case, so if we're looking at a dual core single socket with hyperthreading, it will actually present to the virtual machines a total of four virtual CPUs. And it doesn't, the guest OSs themselves have no idea that these are hyperthreaded processors, or that it's a logical CPU versus an actual physical thing. To them, it looks as if it is a single core non-hyperthreaded processor that's provided to it. And so it says here that hyperthreading enables a core to execute two threads at the same time. That's not entirely true. what happens is it allows them to be queued up. You actually cannot run two threads at the exact same time on a processor. There's a scheduling mechanism that happens there. So if you have a dual core single socket processor, then you can run two threads at the exact same time on two separate cores. But you cannot run two threads at the exact same time on two separate threads. I'm sorry, on two separate, on two separate hyperthreads, two separate logical processors on the same core. That just doesn't work. It's actually a scheduling process that happens in there. Both the operating system believes that both threads are being processed at the exact same time, but actually there's some slicing and dicing that goes on there. So the CPU scheduler itself will process a little bit of the first thread, and then it'll pause and it'll pause a little bit of the second thread, and it just kind of goes back and forth like that. So to the operating system, it believes that there are multiple threads being processed at the exact same time, but that's not entirely true. So ESXi kind of doesn't see that as well, and in theory, it happens so fast that it does appear that it's happening at the same exact time. So that's why we can get away with that. Nonetheless, each logical CPU, so a hyperthreaded core, would show up as two logical CPUs itself. And in this example, we have a dual core single socket, so a single physical processor with dual cores on it, and those dual cores are hyperthreaded, so that shows up as four logical CPUs. Now, VMware understands that that two threads cannot actually be processed at the exact same time. So what they do is when you have a dual core or a dual processor virtual machine, it does its best to try to schedule those two different virtual CPUs on two different cores. So if it had just gone in and randomly just picked a logical CPU, it could have easily presented this dual virtual machine over here. Where did my cursor go? So it could have presented this dual virtual machine here, these two processors. It could have easily put them on the same core down here. So this would be one logical processor here would be one of these cores, and this one right here would be another one of these processors here. And since you can't execute at the exact same time, it kind of makes it moot to have this thing be a dual processor virtual machine. You're still going to get better performance than a single, but there's definitely a degradation there. And so VMware understands that, and it does its best, assuming that the cores are available. It tries to put those two different virtual processors here across different cores on the actual physical processors. And that's actually essentially what this slide right here is talking about. It'll try to span them out. It'll actually do its best, not only for a single virtual machine in of itself, but you'll notice the first example here, we have a core right here. So this is two different, same virtual machine, or same ESXi host here. And we have two different physical sockets. Each of those physical sockets has two cores on it, and they're hyper-threaded. So we have a total of four logical processors per physical machine, and we have a total of 8 virtual CPUs that can be presented in this case. And so on the first processor, it's gone through, and we have a single processor virtual machine. We assign it to this first logical processor here. Then the second one comes along, and rather than assigning it to that same core, it knows that this is a hyper-threaded processor, so let's grab a different logical CPU on a different core, and it assigns it there. And then we're actually out of cores or out of logical processors here, so it just grabs this one. Then the dual virtual machine example that I had here, you'll see that it takes a logical CPU from this core, and then rather than grabbing this first logical CPU, it goes to the second core to try to keep those two processors on separate cores themselves. So hopefully now you can discuss CPU and memory concepts in a virtualized environment. Hopefully you can describe what overcommitment means and identify some of those technologies that are used to improve memory utilization. That's the swap file, the host-based caching, the memory balloon, and the transparent paging. And hopefully you can also describe the how virtual SMTP works and how hyperthreading is utilized by the VM kernel.